Record. Okay. So I guess we're on to homework 3, which we started on Wednesday. I think I have a hard time remembering what happened if it didn't happen in the last 5 minutes. So I'm just going to click somewhere random and we're going to see what's there. Does that sound like a plan? All right, let's go for 1842 in the college people's assignment. I guess I should just say Cindy and Colby instead of college and university people now. Okay, so we got a 10 microfarad parallel plate capacitor connected to a 16-volt battery. After the capacitor is fully charged, the battery is disconnected without a loss of any charge on the plates. The voltmeter is connected across the 2 plates without discharging them. What does it read? And what would it read if the separation is doubled? So we actually haven't talked about capacitance yet. So let's talk about that right quick. So let's just do the parallel plate capacitor, which we kind of did once already, but let's do it one more time. So if I got 2 parallel plates, I got a positive charge on one, negative charge on the other, and this is D apart. Well, we said as far as the potential difference, potential is the integral of E dot dx, which since the electric field's constant, this is just E times D, right? Okay, the other thing we need to remember is, hey, what was the electric field for a parallel plate capacitor? I mean, do y'all remember what the electric field between the 2 infinite sheets was? No. So it was, unless there's a 2 in here, I don't think there is. It was sigma over epsilon naught, where sigma is the surface charge density. Which is a fancy way of saying, hey, it's charge per unit of area, right? So you would have altogether, if you replace this with charge over area, this would be Q times D over area times epsilon naught. All right. Okay. The point of it is, if I kind of try to separate the electrical stuff from everything else. So if I get this Q and this V on one side together, get everything else on the other side, I have Q over V would be A epsilon naught over D. The point of this kind of has like charge and electrical stuff in it. This stuff doesn't. This is just like area and distance. I mean, the A is the area of each plate, D is the distance between them. So this side, epsilon naught is the 8.85 times 10 to the minus 12, which that is kind of an electrical thing, but that's, again, this is the, I can never remember if it's, I get permittivity and permeability mixed up. This one's permittivity.
I don't remember.
I'm going to put permittivity.
Just put perm dot.
Okay. This is the perm of, except my pen won't write for some reason, of free space or of a vacuum.
It's permeability.
It's permeability? Okay. Permeability. All right. Not like you can actually read me trying to fill in the word later. Yeah. So basically, I mean, we talked about this before, but a lot of the theme of physics in general is like resistance, like mass of an object is kind of how much does that object resist being accelerated. Charge of an object is kind of like, okay, well, how sensitive is that object to electromagnetic forces? Permeability is if you've got a substance, it doesn't really want to form an electric field inside of it. So there's a certain amount of energy that it takes to form an electric field inside of anything. So that's kind of how much just a vacuum resists having an electric field put in it. So anyway, okay. So the point is, I mean, kind of this ratio of charge per potential difference, it doesn't depend on anything electrical. It only depends on the shape of the capacitor itself. It depends on the area, the plates, depends on how far apart they are. So this Q over V, this is the definition of capacitance. So, which this formula is just for a parallel plate capacitor. You can work it out for capacitors of any shape, and I'm not going to do that. You will have problems in your homework. I know Colby does. I think Cindy does too, where it'll have like maybe a capacitor built as a cylinder or as a sphere. But I mean, it's the same basic premise. You'll have like two spheres, and they're one slightly bigger, and you're looking at the space in between them. Then the formula will change. Working it out is a pain in the backside, but all of them are actually worked out in the book. So when you find those problems in your homework, just go to the book and find, hey, where did it work out the formula for a cylindrical parallel capacitor or whatever, and then just plug in numbers. So, okay, I guess one more thing about capacitance. Like anything, it has units. The unit is a farad, which is an F. And in real life, a farad is very, very large. So usually we're going to be working either with nanofarads or microfarads. It's very common. It's very rare to have something that actually has like 2 farads or something for capacitance. That would be extreme. So, all right. Let's